Hi, welcome back. Um, I guess you're wondering why I've gathered you here today. We are going to be staging an intervention. Uh, what I mean by that is we are going to be looking at the real world and changing some aspect of it. And we're going to use this power of mathematical modeling to predict what's going to happen in the real world when we change some aspect of it. So, um, we're in this situation. Let's think about where we are as mathematical modelers up at this point. What we've done is we've set up an SIR model. And what we've decided is that the SIR model that we've come up with is a good model. So we've found the best values for our parameters beta and gamma. We've found the best states for our model. So maybe we have the susceptible population, maybe the infected people come in multiple different ways. Maybe we've got a recovered situation. Maybe we've also introduced, there's some amount of people who have died. Maybe there are some zombies. You know, you found the best way to represent this whole situation, the whole way in which the disease spreads throughout the population. And we're at a point where we've found that this model that we've created now describes the situation well. So what do I mean by modeling the situation well? I mean that when you run the model, the output or the results or the metric that you've collected, they match the real world data that you have. So when we've set up our model, we collect it, we run our simulation, the charts that we get seem to match what's happening in the real world. If we're at that situation, we now have a model that represents the real world well. And so what we're going to do now is we're going to add some interventions and determine how a change in the real world behavior is going to affect the output or the results or the metric. So we'll now add an intervention or two or three into the model. And our goal is going to be to say, determine how a change in the real world situation will affect our output, our results, our metric, so that we can make decisions from a policy point of view. If our goal is to, for example, reduce the number of infections, then we can make a decision about how that's going to, how our various different interventions we might do is going to reduce the number of infections. All right, so the example that is probably on a lot of people's minds is the idea of immunizations. All right, and so what I'm thinking about here is we've got some susceptible part of the population, we've got some resistant part of the population, we've got some infected part of the population, and what we'd like to do is we'd like to immunize some people. Let's immunize some susceptible people. So let's say there's some number of people in S that we give a vaccine to. And to model giving people a vaccine, we move people from S to R. So we take a certain block of people who were in S and we move them into R. So why does this work? Why do we do this? So when somebody gets vaccinated, then they can't get the disease. They can't get the disease. And they can't infect anyone. And so they act like a recovered person or a resistant person. All right, so what we're going to do is we're going to create a function that does this. So it's going to move people from S into R. All right, so we're going to define a function called add immunization, which brings in, we need our system object, and we need our fraction. And so this fraction will represent the fraction of the population that was given the vaccine. So what is this going to do? What do we need to do? We need to take some number of people in S and move them into R. So we get our system dot init dot S, and we're going to take some fraction of people away. And then if we take system dot init dot R, we add that fraction in here. All right, and so what this does is it does exactly this moving of people from the S camp into the R camp. Right, and so then our question becomes, how does this impact the model? How does this impact the output, results, metric? So we can think about this in two different ways. We'll do one now and we'll do one later. So we're going to compare two different values. So we can compare with immunization and without immunization. And what we'll do next time is we'll talk about running a parameter sweep to compare many different values. All right, so here's where we're at this point. We have our code that calculates the metric that we care about. Let me copy this, bring it down. Oh, there we go. All right, here's our initial code. This was the code that runs, and I'm going to paste another one down here. So this code up here, this code here, this was our code from before. This calculates the number of people infected without our intervention, without immunizations. All right, and so now what we're going to do is we're going to take this code and we're going to add in our intervention. What does it look like to add in our intervention? That just corresponds to adding in one line of code. And let me change the color here. Change it to red. And then we're adding in one line of code here that does this intervention. We add in our immunization, and we'll immunize, for example, 0.1 or 10% of the population. And the question is, how does that change the total number of people who got infected? All right, so let's go over to Python and calculate that to see how it happens. All right, here we are in Python. We've got, we're including everything that we need. ModSim, we're downloading the information from the previous chapter where make system, update function, and run simulation were defined. If you feel more comfortable, bring those in yourself. Keep them in the same file, but this is how we can import them from the other folder, from the other file that we created. Here is our function that we created that defines the calculate the total number of people who were infected. And this is our add immunization. Remember, it removes some fraction of people from S and adds them into R. And so what we're going to do now is we're going to compare what happens when you look at the system in terms of with immunization and without immunization. So we're going to use our same beta and gamma that we had before, and we're going to create our system object. We're just going to collect the information about our metric, how many people were infected, and our metric gives us that we are at 46.8% of people who got infected in the first example. So now what we're going to do is we're going to add in the immunization. So I'm creating a second system object. I'm calling it system2, and I'm adding in the immunization. And we're running the same simulation, we're calculating the same thing, but now everything's with system 2, results 2, metric 2. And when we do that, we've gone from 47% of the population who got infected down to 30.6% of the population, which that's pretty amazing. Immunized 10% of the population, we've reduced like 7 additional percent of the people didn't get the disease because of this immunization. So I think it's also really good. We've run these two simulations. We can now plot the number of susceptible people over time from using the results.s and results2.s. So we can put them on the same graph. And when we put them on the same graph, what we get is we get this picture. So we started off with almost 100% of the population susceptible, which went down to about 50% of the population susceptible. That's the 46% of the people who got infected in the first case. And then if we talk about immunizing 10% of the population, then we've decreased the number of susceptible people at the beginning, but in the end, the number of susceptible people is higher because a lot fewer people got infected. All right, so next time what we're going to do is we're going to say, what if it's not 10%? What if it's some other percentage? And then how does that affect the number of people who got infected? How does that impact the number of people who got infected? All right, we'll do that next time. I will see you then. Ciao.